Welcome everyone. This is a live streaming discussing and covering our first three episodes, episode 1, 2, and 3, mainly covering the universe, where it started, when it started, and how it looks now, and explaining how we came to know about all this knowledge. So let us start. Our first slide is talking about the visible universe. The visible universe is a sphere with radius 46 billion light year. You can see the red pointer. The blue circle here represents the limit of the visible universe. When we talk about the visible universe here, we refer to the farthest galaxy or star where we received light from. But this does not mean this is all the universe. All the universe is calculated, we couldn't see it of course, is calculated to be at least 500 times this visible universe. So if 46 billion light year is the radius of the visible universe, then the radius of the minimum radius of the overall universe is 23 trillion light years. If we want to present that in a graph, the size of the visible universe is a small dot you see here just on the top left of this pointer. See, there is a small green point there. This green point presents the visible universe, which is having a diameter 92 billion light year, and with 500 times more, the overall universe come around this circle here. If you can see the pointer here and here, this is the overall universe, which is 500 times bigger than the visible universe, with a diameter of 46 trillion light years. As we discussed earlier, the universe is expanding, and we learned that the expansion speed of the universe expansion rate is 20.66 kilometers per second every 1 million light years, which means you are standing here on Earth and there is a star or a galaxy away from Earth about 100 million years, then its expansion speed, the speed running away from Earth, is 20.66 kilometers per second. If we stand at a star or a galaxy, which is 2 million light years, then we add 20.66 multiplied 2 gives us 41.32 kilometers per second. Also, after another 1 million light year, which means for a distance of a galaxy or a star at a distance of 3 million light year, the expansion speed or the running away speed from Earth is 161.98 kilometers per second, and so on. Knowing this, we could simulate that by saying that this black circle here is a visible universe, radius 46 billion light year, and beyond it comes the overall universe. And here, what on this dotted line, we could say this is the point where the universe emitted its first light, which means At this point, when the universe was 380,000 years, this is when the universe emitted its first light. We'll see later why it was dark before. The light from this point started traveling to Earth, but the space between Earth and this point, which is the edge of the universe at 380,000 years age, continued expanding until it reached here today. At this moment, the light which started traveling earlier, due to this expansion, just reached Earth, our planet Earth now. If you see here, this is a timeline explaining how the universe starting from a point which is very, very, very small. When we say small, it's not the size of a raindrop, it's not the size of an atom, it's not the size of an electron, it is much, much smaller even than one electron. We cannot say it's a 0 point because our calculation couldn't reach to that far. This beginning of the universe is behind our calculation and our experiments, but it is a very, very small point. And from that point, the universe started expanding. It was dark until 380,000 years when it emitted the first light. You see this green color and blue and so on. This is the first light emitted by the universe, which we scanned all over the surrounding of our planet, and to give us this shape. And this is called CMB, Cosmic Microwave Background. It's the remaining of the first light emitted by the universe. Before that, the universe was very, very hot, higher than 3,000 degrees Kelvin. At these high degrees or temperatures, the electrons are not able to stay within the orbit of the neutrons or the nuclei of the atom. Thus, making the whole universe is just like a big soup of electrons, protons, and other atomic particles, all running very fast, chaotic, in a way that the photon light cannot find its way. So there were photons, but they were all scattered, so the whole universe was so dark. Only when the temperature of the universe reached 3,000 degree Kelvin, which was at the age of 380,000 years of the universe, only then atoms started to develop, started to form, collect all the electrons around it, and leaving way to the photons to pass through. And then that was the moment where the universe gave light for the first time in its history. This light has traveled to us, as we explained before. Come back to the slide. Yes, this light has traveled to us. From this point it was emitted, but this point was traveling all the way to here during this time from 380,000 years until 13.7 billion years, which is the age of the universe now. And then this light has reached us only now that we can collect it as the microwave background. The microwave background, actually, when it was emitted, it was not in a microwave radius. It was, as we can see here, the light spectrum we can see is only from violet up to red, down to red. And then below that there is the infrared light. Then there is the microwave light. What is the difference? The wavelengths. The wavelength of the microwave is in the range of 10 minus 2 meter, and the wavelength of the visible light 0.5 multiplied 10 to minus 6 meters. So to understand this, let us imagine that we have elastic surface, rubber sheet, and we draw a wave on it with a certain wavelength. And then we stretch this sheet. What happens when we stretch the sheet? The wavelengths drawn on it will get longer, and this is what has happened. For the space between come to the slide. For the space between the universe when it was 380,000 years and Earth, which has been stretched all the way to here, the wavelength traveling here has stretched all the way to make the light wavelengths which was emitted by the universe at that time to be in the microwave range. So it came from this range here, visible light, to this range. And this microwave background light is what we all experience when we used to open the TV in old days before the satellite and 24-hour broadcasting. In these early days, we used to open the TV at 5 o'clock p.m., 4 o'clock p.m., because before that there was no broadcast. And if you open the TV earlier than the broadcast, you find on the screen of TV something like many dots, black and white, like many ants are running there with a sound whoosh, like that. Actually, what we used to see on our old TVs is nothing but the microwave background radiation, this radiation hitting our TV antenna and appearing in our screen. This radiation has been measured very accurately to the most accurate possible way, and has been found to be having little variation in temperature. This is a temperature map, by the way. The universe temperature is around 2.7 Kelvin. 2.7 degree Kelvin means very, very, very cold, very near to the absolute zero, but still not zero. And these variations between the blue point and the red point, passing to the yellow and the green and so on, all these are temperature variations, which was very, very tiny. Tiny in a way that after 13.7 billion years, still in the fraction of 1/1000th of a degree Kelvin. And this very little variation was responsible of forming of different stars and galaxies and all the formation we see in the universe. This little difference. As an example also for to explain how the universe was dark before, when it was hotter than 3000 degree Kelvin, is the fact that the light coming from sun to earth, the photon which is traveling from the sun surface to earth, take around 8 minutes to travel from the sun surface to the earth. But the same photon would need 150,000 years to travel from the center of the sun to the outer edge of the sun. Why is that? Though it is much small distance, the reason is the high temperature in the core of the sun, causing that the material there is just like ionized hydrons electrons are free, everything there is moving very fast, so the light is finding very, very big difficulty to travel through this distance. Take it 150,000 years to do this trip. A question might arise now, talking about how come that we know about this start of the universe, how we know that the universe is 13.7 billion years, how we know that it was so hot, how we know that it was dark before, and so on. In fact, the answer to this comes from this fantastic scientific achievement. What we see here is a plan of the Large Hadron Collider. Hadrons are atoms without electrons, which mean they are the nuclei of the atom, and in case of the hydrogen atom, it's just one proton. So what we see here is a tunnel which is underground between Italy and France, the area where, between France and Switzerland, in the area where the three countries, Italy, France, and Switzerland, are meeting together. This circle length is 27 kilometers. Okay, so they start by accelerating a beam of electrons, a beam of protons, of hydrons in this circle. If you go to the next slide, you see how this tunnel look like from inside. This is how it look like from inside. Inside this tube, there is a very concentrated beam of protons held together by magnets, super magnets, which are super cooled to concentrate the beam of protons around itself, very near, focus it in one center, and make it travel very, very fast through this tunnel all the way. So it makes several circles here, several rounds here, several rounds, and then start from here, and another one start from there, until they meet together and collide together. That's why they call it the Large Hadron Collider, LHC. When these hadrons, these protons collide together, they smash themselves into smaller particles. So we know now, due to this, based on this information we got from these colliders, we know now that the proton is not the basic element of the atom. We know that the proton consists of quarks, and the quarks are held together with gluons. All this information we knew applying this, studying these smashed parts from these collisions. We'll go in the next episodes more about the details of how we could, what we learned from this collider, what is the basic build of the material, what is the basic forces we have, and what are the rules or equations governing them. Here I would like to mention that at these points of collision, locally the temperature rises up due to the collision to values never been in the universe since its beginning. We could reach to temperatures were available only in the universe only when it was at the age of 1 fraction of a second. This fraction is 1 divided 10 to the power of 13. which mean at a very, very, very age, not in the first second, but not in its first half, in its first 1 divided 10 trillionths of a second. This is really mind-blowing to know that we could reach such temperature, available only in the universe at such early age. So this Hydron collider has been upgraded several times, and every time we upgrade it, we add power to its magnets, we add power to its initiator in a way that it could reach with this proton beam speeds very, very near to the speed of light. We could drive through this tunnel the proton beams in a way that it reaches speed. If it is running in a race with a real light, for one complete year, after 1 year, the light will be able to be only 1 meter faster, 1 meter faster than this Hydron beam, this proton beam. So we reached very, very high speed, very, very near to the speed of light. We didn't reach the speed of light yet, and it will be impossible to reach there, but we are very, very, very near. Really mind-blowing what's happening there in CERN. We call it CERN, C-E-R-N, Large Hydron Collider. We'll have a special episode, maybe more than one, about this marvelous scientific achievement we have there. What's going on there really is making history. One thing I want to add to our session today, which is regarding where the Big Bang happened. We go back to the slide. Yes, this one. As you see from this illustration, there was a point in the universe where it started expanding and to reach the universe how we see it now. Where was this point? Where it is related to planet Earth. To our surprise, to everyone's surprise, planet Earth lies in the center of this point, which means the Earth is the center of the universe. Of course, when the universe started, there was no planet Earth yet, there was no solar system yet, but planet Earth happened to exist at the center of this universe. How we knew that? You remember this slide here when we talked about the universe expansion? We measured the universe expansion in this direction, we find these results. We measure the universe expansion in this direction, we find the same results. We measure the universe expansion in this direction, we find the same results. In every direction around our planet Earth, the expansion of the universe is identical. Which means that when we measured the expansion for a certain star or galaxy at a certain distance from planet Earth, say we are having a galaxy here. Let's change the color. Okay, this is better. So if there is a star or galaxy here, and we are measuring the speed of expansion of this galaxy from planet Earth, which is also in a radial direction, we find, for example, that it is 500 kilometers per second. Okay? We just turn to another point with the same radius, another place, and we measure there the speed of expansion away from planet Earth. We find that it is also, if you are standing at the same distance from planet Earth, again, it's 500 kilometers per second. We go to the other direction, same radius, which means the same distance from planet Earth, and we measure what is the speed of expansion there. We measure it and we find it's also the same 500 kilometers per second. In all direction we repeated that and we find always the same result. Same result means for the same radius or distance from Earth, the expansion speed is the same. This happens only if the Earth is at the center of the universe. Though we don't know that the universe, how big is the whole universe, we know only its minimum size, and its minimum size came from the fact or the calculation from the Big Bang, which is stating for the minimum size of universe to be stable, to have a stable universe, that it does not collapse, that it can continue the way it continued for 13.7 billion years and appear to continue much more after. You need to have mass in it at least 500 times the mass you have in the visible universe. So this gives us a minimum point. And this minimum, by the way, is changing every time we repeat our calculations or have better readings, better data, more accurate equipment, more accurate measurement. Every time that is adjusted, it started by 250 times as the first calculation started, and slowly it increased to be 500 times now. In future, this number can be more adjusted, could become bigger, could become smaller, whatever. The more data we have, the more accurate equipment we have, the more accurate number this number will have. But this number always remain the minimum. What is actual, we don't know yet, and we may never know. But there is no also proof that it is infinite. Why I say that? Because it's very, very difficult to prove that anything is infinite. Because we are finite, so how you can measure something infinite? So the fact and the data now say that this universe has a size, has a minimum size, has a visible universe size, has a minimum overall size, but we don't know exactly the overall size of the universe. And with this data on hand, with this data on the table, planet Earth is the center of the whole universe. I'm talking about planet Earth and the solar system and the whole galaxy maybe, because also our reading for these speeds of expansion has an accuracy at the moment. And regarding the size of the universe, the center is having a certain accuracy. What we measured having a certain accuracy, that we could say that yes, Earth is within the center of the universe, within the accuracy we have in our measurement. I hope this discussion is of value to you. I hope that I could put more light on the ideas we discussed before. I'm glad to have you with me today. I hope that we have further episodes, further explanations. We want to discuss this subject of the Earth at the center of the universe more. We want to discuss what we need at the micro world. Instead of going into the outer universe, we go now deeper and see our matter, atoms, electrons, and all the quantum worlds with its wonders, a lot of wonders there. And I hope this will be an enjoyable trip to you, as it is very enjoyable trip for me. All the best. Thank you for having you with us, and see you next episode.